So this time I will be presenting string theory. So what is string theory? String theory is a theory in particle physics that attempts to merge quantum mechanics with Albert Einstein's general theory of relativity with an overarching framework that can explain all physical reality. So it tries to do so by positing that particles are actually one-dimensional, string-like entities whose vibrations determine the particle's properties, such as their mass and their charge. So the image on the left, bottom left, is an image of Albert Einstein, who came up with the general theory of relativity and has made many contributions to particle physics. And the image on the right is a aesthetic depiction of a string that is proposed from the string theory, because there aren't any actual pictures of strings and this theory has not been proven yet. So string theory is one of the proposed methods for producing a theory of everything. So a model that describes all known particles and forces, and that would supersede the standard model of physics, which can explain everything except gravity. So many scientists believe in string theory because of its mathematical beauty in their sentence. So the equations of string theory are described as elegant, and its description of the physical world are considered extremely satisfying in a mathematical language. So again, the image below is a aesthetic depiction of a string. So the theory explains gravity via a particular vibrating string whose properties correspond to that of the hypothetical graviton, a quantum mechanical particle that would carry the gravitational force. That the theory bizarrely requires 11 dimensions to work, rather than the 3 of space and 1 of time we normally experience. The 3 of space being up, down, left, right, and below and forward. So this has not been dissuaded physicists who advocated. So they've simply described how the extra dimensions are all curled up in an extremely tiny space on the order of 10 to the negative 33 centimeters, which is small enough that we can't normally detect them according to NASA. And the image provided below is a aesthetic depiction of a gravity. So gravity is supposed to be a, they're supposed to form like wave-like particles, and the two planets there are neutron stars that are attracted to each other's gravity and forming these wave-like characteristics. So researchers have used string theory to try to answer fundamental questions about the universe, such as what goes on inside the black hole, or to stimulate cosmic processes like the Big Bang theory. And some scientists have even attempted to use string theory to get a handle on dark energy. And dark energy is this mysterious force causing an acceleration on the expansion of space and time. Again, the image provided below is another depiction of strings in string theory, one-dimensional entities that vibrate. And so string theory's timeline. This counterintuitive idea was first developed in the 1960s and 70s, when strings were used to model data coming out of subatomic colliders in Europe, according to a website about string theory created by the University of Oxford and the British Royal Society. So strings provided an elegant mathematical way of describing this strong force, one of the 4 fundamental forces in the universe, which holds together the atomic nuclei. And the image provided below is an image of the British Royal Society and the University of Oxford. So the topic remained marginal for many years until the quote unquote string theory revolution in 1984. So when theoreticians Michael Green and John Schwartz produced equations that showed how strings avoided certain inconsistencies, plaguing models that described particles as point-like objects, according to the University of Cambridge. And this is an image of the 2 scientists, Michael Green and John Schwartz. Well, but this first flowering left researchers with five different theories explaining how one-dimensional strings oscillated in a 10-dimensional reality. So a second revolution came about in 1995 when physicists showed that these differing ideas were all related and could be combined with another theory called supergravity, which worked in 11 dimensions. And that approach generated the current incarnation of string theory. And the image provided below is, again, a depiction of a string. But string theory has lately come under greater scrutiny. So most of its predictions are untestable with current technology, and many researchers have wondered if they're going down a never-ending rabbit hole because strings are so tiny to observe. So in 2011, physicists gathered at the American Museum of Natural History for the 11th annual Isaac Asimov Memorial Debate, who is a writer and a futurist, to discuss whether it made sense to turn to string theory as a viable description of reality. So Neil deGrasse Tyson, the person in the picture provided below, is a physicist, was also the director of the museum's Hayden Planetarium, and he pointed out that progress on string theory had been patchy in the previous years. And he teased his crowd by saying, quote unquote, "Are you chasing a ghost? Or is the collection of you just too stupid to figure this out?" So, why is string theory so hard to prove? Well, the most recent challenges to string theory have come from the framework itself, which predicts the existence of a potentially huge number of unique universes, as many as 10 to the 500. And that's the number one followed by 500 zeros. So this multiverse landscape seemed to provide enough possibilities that should researchers explore them, they would come across one that corresponded to our own version of reality. But in 2018, an influential paper suggested that not a single one of these myriad hypothetical universes looked like our cosmos. Specifically, each lacked a description of dark energy as we currently understand it. So, as Marilena Lovert, a physicist at Stony Brook University, says, inflation is the most compelling explanation for why our universe looks the way it does and where the structure came from. So inflation explains how, in a sense, we got everything in the universe from nothing. So the theory says that the early universe went through a phase of extreme expansion, and the process magnified random blips in the quantum vacuum and converted them into galaxies and other stuff around us. So theorists have had a difficulty showing how or if inflation works in string theory. And the most promising road to doing so, the KKLT construction, does not convince everyone. And the image provided below is of Marilena Loverd. So in 2018, a group of string theorists took a series of suggestive results and argued that this difficulty reflected an impossibility. So that perhaps inflation just cannot happen in this string theory. So this called the Sitter-Swampland conjecture, which claimed that any version of the concept that could describe the Sitter space, which is a term for the kind of universe in which we expect inflation to take place, would have some kind of technical flaw that put it in a so-called swampland of rejected theories. So no one has proved the swampland conjecture, and the several string theorists still expect that the final form of the theory will have no problem with inflation. But many believe that although the conjecture might not hold up rigidly, something close to it will. And any limit on inflation would raise the prospect of testing string theory against actual data, but a definite test requires a proof of the conjecture. So according to Carmen Waffa, a physicist at Harvard University and one of the swampland conjectures authors, researchers can start to build a case for the idea if they can connect it to trusted physical laws. And again, the image is a depiction of the strings in string theory. So string theory's applications. An exciting application of this string theory actually takes place in the context of condensed matter physics. So there's very deep correspondence in physics called the gauge gravity or the ADS CFD correspondence. One on one side, the correspondence on one side of the correspondence, you have gravitational theory in d dimensions. That's usually described by string theory. While on the other side of the correspondence, you have specific quantum fields in d minus one dimensions, but no gravity. So the latter is considered as being the boundary theory of the former. The image below it essentially depicts this idea. So the discovery of this correspondence has been one of the biggest revolutions in theoretical physics, as it can be used exclusively as a mathematical tool that makes calculations easier. In particular, some calculations are much easier to do on one side of the correspondence than the other. So this correspondence has been used in many fields of condensed matter physics. And for example, the University of Utrecht and the University of Cambridge have research groups applying the correspondence to the field of topological materials, which exhibit the new famous quantum Hall effect. Another example is the study of strange metals. A book that covers this quite comprehensively is called The Holographic Quantum Matter, if you're interested. The author is Hartnell, Lucas, and Sachdev. So it was even used to explain some recent experimental results that no other approach has been able to explain. And this topic shows how string theory can indeed find applications to fields of physics that have direct contact with experiments and yield new results. And these are the citations for this presentation. Thank you for listening.